In this third class of the automotive air conditioning course, we will focus on the condenser, also known as the system's external coil. This component is essential within the vehicle's refrigeration circuit, as it is responsible for dissipating the heat coming both from the cabin and from the refrigerant compression process. Understanding its operation, characteristics, and possible failures allows the technician to perform more accurate and effective diagnostics in automotive climate control systems. Location and function of the condenser. The condenser is installed at the front of the vehicle, right in front of the engine radiator. Its strategic position allows outside air to flow easily through its fins, promoting proper heat dissipation. At this stage of the circuit, the refrigerant circulates at high pressure due to the previous compression. The compressor sends the refrigerant in a superheated vapor state, the highest temperature in the entire system, directly to the condenser. Here, the heat transfer required for condensation takes place, meaning the transition from vapor to liquid. The system fan brings fresh air from the front of the vehicle toward the condenser. As this airflow passes through its fins, it carries away the heat being released, ensuring efficient operation even when the vehicle is stopped or idling. Remember that in the video description you will find the link to the evaluation for this class, types of condensers used in automotive air conditioning. 1. 3/8-inch tube and fin condensers. This classic design uses 3/8-inch copper tubes with aluminum fins. It was very common until the 1990s due to its simple construction and low cost. Advantages: compact and lightweight structure with good mechanical strength. The lightweight materials make installation easier and reduce costs, while the robust construction ensures a long service life. Repair: easy to repair using traditional techniques, copper soldering or tinning. Small leaks can be welded or patched with basic tools, and damaged fins can be straightened or replaced, making these condensers repairable in the field by most workshops. 2. Serpentine condensers. Introduced in the 1970s, they are made entirely of aluminum with a single continuous serpentine-shaped tube. This increases the heat exchange area and reduces weight compared to tube and fin designs. Advantages: being pure aluminum, there is no galvanic contact or mixing with copper, improving resistance to external corrosion. Their long corrugated tube maximizes surface contact with air, improving heat dissipation. They are also lighter and occupy less space than older copper condensers. Disadvantages: they are less efficient than modern parallel flow designs. In fact, the parallel flow microchannel condenser exceeds their efficiency by approximately 25%. 3. 6mm condensers, or piccolo. They appeared in the 1980s to improve efficiency by using very small diameter tubes, or 6mm. Advantages: by using smaller and multiple tubes, they significantly increase the refrigerant-to-fin contact surface. This increases heat transfer capability compared to larger tube condensers. 4. Parallel flow microchannel condensers. This current design uses flat aluminum tubes with internal parallel microchannels. Introduced in the 1990s, along with the shift to R134A, it is the most efficient and widely used today. Advantages: their architecture provides optimal heat transfer, improving thermal efficiency by about 20 to 30% over traditional condensers. They are compact and lightweight, and because they are monolithic, a single aluminum block, internal leaks are minimized. Corrosion resistance is very high, treated aluminum. Refrigerant compatibility. Designed for R134A from the beginning, and in modern systems also for R1234YF. The materials, aluminum and high-pressure seals, support both refrigerants. In fact, all new systems, including hybrid and electric vehicles, use parallel flow condensers due to their performance with R1234YF. Remember that in the video description you will find the link to the evaluation for this class, where you can reinforce what you've learned and test your understanding. High side pressure. As mentioned, the system also operates with high pressure corresponding to the compressor outlet toward the condenser. At this stage, the refrigerant arrives as superheated vapor, 100% vapor, and must be cooled until it returns to its liquid state. When the condenser's heat exchanger is working correctly, the temperature at the midpoint of the coil should be approximately 15 degrees Celsius or 27 degrees Fahrenheit higher than the ambient temperature. For example, if the ambient temperature is 35 degrees Celsius or 95 degrees Fahrenheit, the average condenser temperature will be about 50 degrees Celsius or 122 degrees Fahrenheit. With this information, we check the high side gauge on the R134A scale and determine the ideal working pressure. In systems that use R1234YF, the same procedure is performed using the appropriate gauge for that refrigerant. Remember that in the video description you will find the link to the evaluation for this class. Most common failures in automotive condensers. 1. Refrigerant leaks. The most frequent failure. Causes: corrosion from moisture, salt, or mud. Impact from stones or road debris. Vibrations that crack joints or microchannels. Symptoms: low system pressure. Poor cooling performance. Oil stains on the condenser. 2. Internal blockage. Very common in microchannel condensers. Causes: metal debris produced by compressor failures. Moisture generating acids inside the system. Use of incorrect oils or refrigerants. Symptoms: high pressure on the high side. Poor heat transfer. Weak or warm air inside the vehicle. 3. External blockage, dirt and debris. Affects even systems in good condition. Causes: insects, leaves, dust, or mud. Oil buildup that traps dirt. Symptoms: high side overpressure. Fan working harder. High pressure switch activation. Intermittent cold air. 4. Physical damage from impact. Causes: minor front impacts. Road stones. Misaligned grille or bumper. Consequences: bent fins, reduced airflow. Broken tubes, leaks. Crushed microchannels, internal restrictions. 5. Insufficient ventilation. Causes: weak or faulty electric fan. Damaged relays or fuses. Failures in temperature or pressure sensors. Blocked radiator or condenser. Symptoms: rapid increase in high side pressure. Cold air only when the vehicle is moving. Compressor shutdown for safety. Corrosion. Common in coastal or humid environments. Causes: salt, chemicals, and contaminants. Moisture trapped between the radiator and condenser. Low-quality aluminum.